Hello everyone, this is the part 2 of the first tutorial of the setting up a heat transfer and fluid flow problem in Fluent, which is the first tutorial of the ANSYS workbench Fluent. So basically we are going to solve this problem. There's a main flow here and there's a mixing flow. In the first part of this tutorial, previous video, we have created this geometry. We have created this main pipe, pipe and this tube kind of intersecting that pipe. So we will close the design modeler, and in this video I'm going to show you how to create mesh and send this mesh to Fluent to do the analysis, CFD analysis using the Fluent. So double click on the meshing. I'm using again ANSYS 2019 R2. You can use whatever version you have access to. So there's no difference in 2019 R1 and R2. The icons has changed a little bit, but not that much of a big difference in the usage. The shapes are changed a little bit, but basically it's the same. So now we have opened our geometry. So let's change the units of the meshing to millimeters, to SI units, millimeters, kilogram, or whatever millimeters it has, whatever units that includes the millimeters as the length. So okay, I will start with the simple meshing and go through some settings and menus in the meshing. The main goal is to go through some menus and for the new users to make it to make the users get familiar with the meshing. So first I will click on the meshing. If you click on the meshing, you will see that because we dragged and dropped the Fluent, it's by default it is kind of physics is CFD, solver is Fluent, linear, and these settings by default are loaded. You can see it's possible to create meshing for other softwares, but it will not then work with the Fluent, so it's better to keep these as is. So I will choose an element size of 3 millimeters. So when you choose an element size, your cursor will be there will be two circles beside your cursor, the maximum and minimum the element size you have set. So if you change it like to 20 millimeters, you will see that the circles are increasing. So I will keep the 3 millimeters. So let's create the meshing with no settings. Like right click on the mesh and create on generate mesh. So first I will go with no settings, like the simplest mesh you can create in ANSYS meshing. So it will take a little bit based on the size and your computational power on the machine you are doing. Okay, meshing is done for this geometry. As you can see, we have a all tetrahedron tet meshes. So let's cut, make a sectional cut, a sectional plane. So there's a option called sectional plane. If you click on this one, and let's click on the x-axis, look at this view. So you can draw a line and see inside the geometry. So it cuts the geometry in half, so you can look inside the geometry. You see that these kind of mesh is generated. So since we are going to simulate a turbulence flow and we will have boundary layer, it's better to resolve the boundary to kind of better capture the boundary layer effect on our simulation. It's better to have some inflation layers. Inflation layers means that we will have a smaller mesh near the wall or boundary, and as we go further, the mesh the mesh size will increase until reach the main mesh size here. So how can we do that? And the one method is to go to the inflation here, where this is none, change to program controlled. So as you can see, we need to redo the meshing. So generate mesh again. So as you add more settings, for example, inflations or more controls, you are kind of limiting the meshing algorithm. So it will kind of take more time as you add more inflation layers or other size controlling or other local size controlling or other elements. So it will kind of override this like default algorithm. So it could take longer to do the meshing in the ANSYS meshing. And if you put wrong settings, sometimes you will not have a like successful mesh, and you will get errors. Okay, now meshing is done and our sectional plane is active. So let's zoom in. As you can see here near the wall, we have like finer mesh, and with some aspect ratio, they are increasing the height of these elements as reaching like we have 5 layers by default, I believe. If we go to the inflations, we have maximum layer of 5 and the growth rate is 1.2. So it means that height of the second layer is 1.2 times the first layer, and it goes up to 5th layer. So one method of adding inflation is kind of activating this inflation, or we can switch it back to none. For example, we want to only create inflation on this small pipe. So let's right click on this one, insert inflation. So for the geometry, let's select, let me go to the section plane and turn off the section plane. So on the inflation details, so geometry, I will select the main body, and boundary, I will select this face of the outer face of the smaller pipe. So let's see the results. So okay, again 5 layers with the same options. Okay, meshing is done. So let's go to the section plane, cut the meshing. As you can see, we don't have the inflations anymore near the main wall, and we have the inflations on the small pipe. So this is the method you can control the inflations. So another method of controlling the mesh size and local sizing is defining sizing. So let me clear the generated data, so it will delete the created mesh. let me turn off this section plane. So and I will delete this inflation for now. So let's say, for example, you wanna have a finer mesh based on your physics in a specific area. You can right click on meshing, insert sizing, and based on the geometry, if you select a face, or you can select an edge, or if you have multi-body geometry, you can select a body. So let's select this edge, for example, or let's go down and select this edge. So, and click apply. The element size is 3, which is the default mesh size. Let's do like 1 millimeter. You can see that there are some line sections around this edge you have selected, kind of representing the number of the elements. So if you click 1 and let's generate the mesh again. So it will create finer mesh around this edge, but we will have smaller mesh closer to this edge too, because in ANSYS we will have smooth transition of the mesh sizing, because we want to keep the aspect ratio of the neighboring elements a small number closer to 1. So as you can see, we have a mesh size of 3 all over the body, and here is mesh size of 1, and it like slowly growing the size unto reaching up to reaching the main default size or main size. So you can change the sizing for the face sizing, body sizing, and etc. So I will delete this sizing. Another method of controlling the mesh is assembly mesh. It's a, this is like if you, for example, switch to cut cell and generate the mesh again, it's kind of another called assembly meshing. It's better to refer to Fluent help and meshing help about the theory of this about the meshing. So as you can see, this created a larger size mesh, and it couldn't like create the mesh. So let's go to the mesh sizing here. So because the default size is 59, let's do the 3 again and generate the mesh again. So cut cell meshing is kind of different method. It kind of cuts geometry and created the size. You can see on this pipe we have smaller mesh size, and it goes to the bigger mesh size, and we have a transition near this area where the small pipe connects to the main pipe. So I just want to show you how the settings are and how we can control the different parts of the meshing. So after this mesh, I will kind of create the inputs and outlets. You can see it's almost mostly hexa or cubic, near cubic size shape mesh, so which is better for our simulations. So you can check the quality. If you go to the quality, so you have you can get different reports on the quality, for example aspect ratio. So the perfect aspect ratio is the one, oh, I might detach this window, okay, let's see, it shows the distribution of the different aspect ratios, and it shows the minimum aspect ratio is almost 1, the maximum is 5, the average is 1.1, which is good. So if you check the skewness, which is the deformation of the elements, which should be less than 90, we have but 96, the minimum is 1 to the minus 10 almost, but the average is very small number. It shows that we have few elements with larger skewness, so it is still good. So it's a good quality mesh. And also we can check the orthogonal quality, which should be closer to 1. The minimum is 0.3, the maximum is 9, the average is 97, which is a good distribution. So we have few elements with bad orthogonal quality, so we can work on that, identify those elements. And since this is a simple simulation, it doesn't matter on our convergence or simulation results. So I will go back to our, I will turn off this assembly meshing. I will turn on the skewness to have a program control, to have a boundary layer inflation near the wall, so generate the mesh. By default, the meshing will create the tetrahedral meshing, which is simplest and easiest way to mesh, but it's not preferable for CFD simulations. So you can, one way is to create tet mesh here and go to the Fluent and convert them to the polyhedra meshes. I can show you later in the next video to how to and compare the simulations, how it's getting faster and better. And numerically, the polyhedral mesh is more accurate than the tet mesh, and in some cases in hex meshes. So you can refer to references about the tetrahedral meshes, polyhedral meshes, to see what's the benefits of those type of the mesh. And also if you use Fluent for meshing, the new Fluent has the meshing, so if you can directly create the polyhedral meshes in Fluent too, which is a very powerful tool. So I will teach how to create Fluent meshes in future videos. So we have our mesh now, and this is the quality of orthogonal quality is still good, maximum 0.99 and average is 81. So also here you can see in the statistics, you can see the number of nodes and the number of the elements we have. This is 1 million elements. It's a quite large number of elements. So I will change. First, I will create the name selections, the inputs, inlets and outlets. You can see we have a flow from here. This will be an inlet, outlet, and this will be another inlet number 2, or we can put another name. So for defining the boundary conditions, we will click on this face, right click on it, and create name selection, or you can press N as a shortcut. So create name selections. Let's put the inlet 1 or inlet underscore main, and click on this one, name selection outlet, because we have one outlet, so I will just name it as outlet. And let's click on this face and create an new create name selections and inlet underscore small. Okay, so now we have inlets and outlets. I will increase the no, I will just keep the mesh size, so you can see it will be a little bit slow in Fluent, so you can convert to polyhedrals and make it faster. So if you refer to workbench, you can see there's a like a thunder shape, something that it needs to refresh. So there's no check mark like the geometry here. So you need to right click on this and click update. So when you click update, it will kind of send all the informations to Fluent. So if you have any changes in your mesh settings, it will regenerate the mesh and send the mesh data to Fluent. So it will generate the mesh and send the mesh data to Fluent. So I will leave the rest Fluent setup for the next video. Thank you for watching this video. Please subscribe to our channel, and you can learn about the geometry creation of this specific problem in the previous video. And in the next video I will talk about setting a heat transfer problem in Fluent, doing some parametric study, and I will expand this exercise or specific problem for more features in the Fluent. Thank you again for watching.